Well, the title is there, and this is about a large European project on variety trial testing. Please, Jip.
I'll assume that applause was not for me, but for a previous speaker. Thanks everyone for joining. Thanks for coming also. It's a very nice symposium, a lot of interesting speakers, and myself. So I'm going to talk about like Fred said, a European project that we've been working on, an INVITE. A lot of people involved. I mentioned a few here, but there's a lot more. INVITE, in short, stands for Innovation in Plant Variety Testing in Europe. It's an H2020 project. It involves a lot of partners listed here. And the sort of general aim of this project is to improve variety testing and the information available to stakeholders on variety performance on the range of conditions. So that's sort of a nutshell the project's aim, and there's a lot of sub things going on. But we look at the analysis part of data that's generated not only in this project but also from historical trials that are done in each country, VCU trials. So just a quick recap. So before a variety is released onto the market, it needs to be tested for their use for the farmers in terms of yield, disease resistance, abiotic stresses, and more. And they're tested in a whole range of environments, and the hope is that environments sort of accommodate the target population of environments. Basically what the previous speakers already have nicely summarized for me. Within this project, so we have several European countries, and each country has its own system, and they're basically not really communicating. They have their own sets of criteria and the way they test things. More or less similar, but there's little communication between countries, and there's no guarantee that the varieties that are released onto the market are necessarily suitable for all environments. Is it me? I'm just giving such a cracking performance here. Yeah, people are pointing. Or should I just take the... It's not a minute. Okay, now I feel like a pop star. Okay. So where were we? Okay, so this is sort of the background. Today we're going to look at the historical VCU trial data that we received as part of this project, and we're going to look at how, basically the efficiency of these currently existing networks for testing, grain yield as the main trait. So we're going to look at G by E, how it is composed in each country, the genetic gain over time, also a way to sort of assess how these VCU systems are doing, and the precision with which each VCU system can detect differences between varieties. And then, of course, the question, can we improve precision in these networks? Okay, so we have access to VCU data for 15, 16 years from 7 countries, and we are talking about maize and wheat here. These are the main crops that are grown across these countries. I'll name them in the next slide. So what we had here is adjusted genotypic means. So we don't have to worry about trial design, spatial effects, etc. So this is just what we have. Basically the blues for each genotype in each trial. So these are VCU data, but they actually also contain, in some cases, post-registration varieties, reference varieties. So it's actually a mix of different types of varieties. So before the project, we requested with the national examination offices a whole bunch of data in a standardized form. But you can imagine if you send out a form to different parties, please do it like this. They all give different responses. We requested several traits. Yield is an important one. Grain weight, oil concentration, you can name a lot of them. Most of them actually only provided yield-related traits. So We're going to focus on yield for today, which is also one of the most important traits. We have varieties which are totally encrypted, so there's also no relatedness information between them, although that information is becoming available. Yeah, so this is sort of summary of the data. I don't want you to look at it, at least study it. Just to mention the countries, we have Austria, Belgium, Czech Republic, France, Germany, Hungary, and Switzerland. And they differ wildly in the number of varieties they test over the years, and also the number of locations that they test. This is just an overview of what the data structure looks like. I was going to say here, this looks very well, but then after hearing Salvador's talk, I'm beginning to doubt. But so basically what you see here is the number of unique varieties in each year and the overlapping varieties between years. And as you can see, it's actually across networks, across countries and crops, it looks pretty decent. So test cycles in these VCU systems, they run about for 2 or 3 years. So you would expect a rather diagonal structure, but like I said, there's a lot of reference varieties, post-registration, and other types of varieties in there as well. So that provides us an opportunity to do some nice modeling. Okay, so we've started by fitting mixed models to quantify the G by E. Well, this looks familiar. We've seen this on previous slides as well. So we have the genotypic mean yield, the blue basically on the left side, and then we model a random genotype effect, location, year, and all the interactions. We don't have any plot level data, so we cannot estimate the error variance, so the three-way interaction between genotype, year, and location, and the plot error variance are confounded. So that's a limitation that we have to work with. To assess the genetic trend, because that's also what we're interested in, we fit a release year effect and a trial calendar year effect as a continuous covariate. That allows us to see how genetic progress has been. This is sort of a general model that we used for wheat. For maize, we have a slightly more complicated data set where we have maturity class. So M here stands for maturity group, not management. And that sort of eats away a bit of the genetic variance. So we need to take into account that as well in the modeling. Okay. Looking at G by E, so this is the pattern, the general pattern that we found across countries. So these different bars are different countries, and I here sorted them by genotypic main effect variance, which is in red. Then we have the GL in gray, GY in yellow, and the three-way interaction residual in blue. And one thing that's quite nice is, I mean, the patterns differ somewhat per country, but the overall pattern is quite similar. Quite a large three-way interaction effect, which indicates, like we see often, that G by E is very trial-specific. And that also makes it challenging to adjust specific things in the system, like testing at different or more locations or different number of years. Now we can express these variance components also as coefficients of variation. And we'll see that genetic effect accounts for about 2. On average, a CV of 4 across crops, which basically means that about plus or minus 8% of mean variance is accounted for by the genetic main effect. So we have the variance components, and then from that we proceeded to calculate the precision of the system. And there, for that we looked at the least significant difference between varieties. So the precision with which you can distinguish between them. So we use the variance components for that. Basically, we have the G by E variance components, and you divide that by the number of years, number of locations, and number of years and locations. Yeah, so ideally, we might also want to look at, what happens if you change the number of replicates, number of blocks, etc. But that information is not available. So we're merely interested in sort of the temporal spatial element of this. From that, you can calculate the SED. And now we expressed the LSD as a percentage of the high-yielding standing varieties. So that sort of indicates the percentage that competing varieties need to differ from each other in order to catch that difference. And also it provides a way for LSDs to be compared between countries because they operate at different scales. So this is a way of standardizing it. So when we look at the LSDs across countries, so here we have wheat, the LSD in percentage here on the y-axis. You see there's quite a lot of variation between countries, ranging from about 4 to 8. So that's the amount, so the precision with which these systems can distinguish between high-yielding varieties. And we see a sort of similar pattern for maize. The order flips around a bit. Different countries come on top here compared to wheat. Yeah, but that's it. So we see the LSDs. We see that they're quite a bit larger than the coefficient of variation that we saw earlier. And that pretty much tells us that these systems, although they pretty much capable of distinguishing good from bad varieties, they're not suited to really distinguish between in the very margins of the yield range. So, is there anything that can be done for these countries to really improve their networks? So, for that, you can play around with the variance components, or actually not the variance components, but the number of years and locations in the equation. And then basically what we see here, if we up the number of years, number of locations, the precision of the systems increases somewhat. And if we go from 2-year testing to 3-year testing, we also further increase the system. But it's all rather marginal. And an important observation that we found for these networks is that currently they're actually testing pretty much, at the optimal number of locations, which is at the elbow point of these lines. So actually these networks are doing quite well. So we also fitted the genetic trend, and across the board this was significantly positive, also strictly linear, so we did not observe any plateauing across this 15-year period. And if we express that as a % change per year, we see that there's some variation, but they pretty much average all around 1% per year, which is actually what we hear from breeders as well, which the number that they aim at. We also fit non-genetic trend, but they were actually mostly non-significant. And but even though they were non-significant, they had estimate effect sizes that were sort of comparable to the genetic trend. So we tried to look into, so is there anything going on in terms of the nitrogen application over time? Has that changed? Sowing dates or any other management practices, but we couldn't really link that to the non-genetic trend. Okay, so now we have precision, now we have a genetic trend, and then we start thinking about what does it actually mean? So what are these testing networks doing, and are they doing it satisfactorily, if that's a correct word? You can think about it from the breeder's perspective. If you think about the time it takes for a breeder to develop a new variety, and I'm going to look at Mark now and see if I have it more or less correct. It takes about 10 years on average, might be a bit less, be a bit more, basically from the first crossings, hybridization, up to all the testing that comes after, say about 10 years. And if you want to have this 1% increase every year, that means that you need to have a 10% differentiation between varieties at the very first stages of testing. And that's actually what we hear from breeders as well, that they actually select varieties that are 10% apart. And then I started looking at our data and see if I can calculate the precision of a single trial using our variance components. And you see that indeed most of them are above 10 or above, 10 to 15 more or less. And given that, so assuming a 10-year variety turnaround time, you can translate into a 10-year genetic trend. And you would expect the observed genetic trends to fall on the XY line. And interestingly for maize, that it sort of happens here. Not so much for wheat, but for maize, it would seem that the precision that we observe in the systems actually generate a 1% genetic increase, which is actually, what breeders tell us that they do and what they want. So this nicely checks out. Just out of curiosity, I looked into the literature as well. I just looked up some papers that looked at various crops that reported variance components and genetic trends. And again, so I computed the precision at a single trial, and then relate that to the expected genetic trend, assuming a 10-year variety turnaround time. And you see that pattern is actually not at all straightforward. I mean, it looks like, and these are only 7 data points, but it looks like European maize testing is doing quite well here. So the bottom line, the VCU testing systems for maize and wheat in Europe, they show sort of similar G and G by E patterns between countries. Precision varies, but they all seem to be testing closely to optimum with respect to the number of locations. Precision could be upped if the wish is to really distinguish between top-ranking varieties. But regardless, we see genetic trends of, on average, 1%, which really conforms to breeders' expectations. So, looks pretty well. I'm not sure how much time I have. Yeah, okay. So, so these are future. So we have 2 more months in the project. So now the bulk of the analysis still has to be done. That's always interesting. So we're looking at zonation, like envirotyping. So there's going to be some talks about that as well. Integrate that into our networks. Problem, of course, is that the connectivity between countries is very poor, but we have relatedness information for wheat at least, so we can play around with that. And then there's the other thing of using environmental information. This is basically the random regression that Hans-Peter and Daniela talked about. We've developed ways or implemented ways to expand this to include the coefficient matrix, so the intercepts and slopes between different zones and connect them. And then even within that, expand to multiple ECs. That's ongoing work, quite nice, and it might be nice to apply to these invite projects as well. I'm going to leave it there, so we ran out of time. Thanks for listening.
Thanks a lot, Jip. I'm sure that a few of these statements will cause a lot of discussion, and I propose that you do that in the break, but there's one question that I can allow now. So is there any specific question that... Renaud. Wait, where's the microphone?
Where?
Renaud. Oh, you don't know Renaud.
Thank you for the talk. So if I understood well, you don't see the effect of climate change, right? You don't see any non-genetic trend. I was quite impressed because in France it's quite visible since the late 90s.
Wheat or maize, there was, I sort of made a general statement, but there was indeed, I think it was for France, I believe it was a negative economic trend. That's true. So there was, but in general, across networks, it was absent. But yeah, you're right. So I had to make a sort of general statement. But like I said, I tried to link that to what happened in like management and harvest dates, sowing dates. But I couldn't really find a link. Maybe we can talk after if you have any ideas why that might be. Yeah. Thanks.
Thank you.
Okay. Thanks again.